Okay, so we're gonna move on to 4.7, which is Maxima and Minima problems. I think it's amusing that the name of the section has the word problems in it. I will warn you that there are not a lot of problems. There's only currently 13 slides, but the answers are pretty long, so we do have separate parts for part A and B at the moment. We might need more, hopefully not. All right, so much like with all things we've been doing lately, the first thing you want to do is find your partials. Um, so I will do the step. So if you work that out a little bit, you end up getting negative 9x plus 18 over the square root. And then we're going to end up doing something with these, so I'm kind of going to do it a little bit weird, and you guys can decide how, like while you're doing your homework, how you would want to approach these. I'm fine if you want to do it all together, so you'll see what I mean in a minute. All right, so the next step we're going to do is we're actually going to set them equal to 0. So then we multiply each equation by its common denominator, and we're going to end up with our negative 9x plus 18 equal to 0, and our 4y plus 12 equal to 0. So therefore, we have x equal to 2 and y equal to negative 3. So then 2, negative 3 is your critical point of your function. We also check the possibility that the denominator of each partial derivative can equal 0, thus causing the partial derivative not to exist. Since the denominator is the same in each partial, we only have to do it for the singular one. Of course, they did that on purpose. Be careful on your homework, they may not, so make sure you check both. So of course we want to know if it's really that. Oh. So if we solve it for 0, which we might as well do on a new slide. Have 4 y squared squared. All right, and then we want to complete the square. So twice. All right. So dividing both sides by a negative 36, we get the following equation in standard form, which would be x minus 2 squared over 4 minus y plus 3 squared over 9 equals 1. So we want to notice that point 2, negative 3 is the center of a hyperbola. Yep. Okay. Alrighty. And now we're going to go on to part B. All right, so first we want to just calculate your partials. So now we'll set them both equal to 0. Sorry, it's going to be a little bit of Christmas. So subtracting the second equation, well, let's rewrite that a little bit then, I guess. So then we'll just subtract So y is going to equal -1. And then if we sub back in, we get that x is also equal to -1. So we have -1, -1. Is the critical point of G. And then there are no points that would cause the partial derivative to not exist. So you can add that if you want. There are no points. Okay. All right, we got some definitions. Just a definition with some stuff on it. All right. Okay. We have a nice little theorem brought to us by Burnett. Just when you think you get away from that guy, shows up everywhere. I knew this slide was going to look pretty gross and ugly, so don't worry about it. You can look at it on the PDF. It'll look better. There was just a lot of stuff that I felt would be good to pull out this time. That way you guys can just look at my PDF instead of having to scroll through the whole textbook. All right. Okay, so step 1 of the problem solving strategy involves finding the critical points of the functions. To do this, you have to first calculate the partial derivatives and then set them equal to 0. So we are going to focus on part A. So the partials are and nope, we just did that one. Okay, and now we want to set them equal to 0. So if we solve this system, which you all should know how to do, we're going to end up getting -1, 2 as our critical point. You guys okay if I use the good old CP? All right, step 2 of the problem solving strategy now involves calculating our directional, I guess, or second derivative. Calculate the second partial derivatives. So okay. So now we want to plug it into the which would give us 8 times 18 minus 0 squared, which is 144. Step 3 states the second derivative test for the two functions. Since d is greater than 0, and your second derivative, negative 1, 2, is greater than 0, this corresponds to case 1. Case number 1. Therefore, the function of f has a local minimum at negative 1, 2. So this is a okay, and I will show you the visual that we have. Okay. Now we're going to go on to part B. Oh, I guess that's a G. In the grand scheme of things, if on your test you get into the flow of just using f as your function instead of G or H or all the other letters of the alphabet, I'm not going to take points off for having I'm not going to take points off for something small like that. And we will set those to 0 and solve. Okay. So if we solve for y, we get 3 minus 2x over 2. And if we substitute that into the first equation, we get x squared plus 2 times 3 minus 2x over 2 minus 6 equal to 0. So you end up with x squared minus 3x minus 3 equal to 0. So x minus 3, x plus 1. So then you're looking at either x equal to 3 or x equal to negative 1. If you shove those answers back in, then y is going to be either negative 3 halves or 5 halves. So those are your critical points. You guys can make them points. I will leave that in your capable hands. All right, I'm going to add a slide here. We'll go back to the visual in a minute. So the next thing we need to do is find our second partials. All We're going to plug that into the formula. Okay. All right, so because we have two different critical points, we have to plug this in twice. Negative. I'm going to trust that you guys can follow along with how to find those. All right. So in step 3, we note that applying the second derivative test for the functions of the two variables. For the first point, the -1, 5/2, this leads to case 3. So that means that this will be a saddle point. You guys will probably see it a little bit better with the visual too. And then applying the theorem to the next point, that leads to case 1. Which means that it would be the local minimum. Okay. All right, so here is your visual. Try to get it in here so you can see it all. There you go. All right. Should be all good. All right, so you have a nice little theorem that you can look at some point. Feel free to read about it. Huh. Right, just one more example to go. It has 2 different parts. So you want to go through and get those notes. Okay. All right, so for part A, there's no real surprise. We're going to find the partials and set them equal to 0. If no one saw that coming, I would be shocked. Okay. All right, and then obviously solving the system is set up very nicely. Just going to go ahead and solve. Oops. So y is equal to 1, which will lead us to x equal to 3. So then that means that our critical point is 3, 1. Calculating f of 3 will give you, or f of 3, 1 will give you 17. The next step involves finding the extrema of the function on the boundary of its domain. So the boundary of its domain consists of 4 line segments as shown in the following graph, and I will show you that right now. I believe it is that one. Yes. Yep, that's the one. Okay. There is a much deeper, more in-depth explanation of that graphic, but the gist of it is you want to find f of 0, 0, which is going to be 24. F of 4, 0 is going to be also 24. F of 4, 2 is going to be 20. And f of 0, 2 is going to be 36. Okay, so the absolute maximum value is 36, which happens here. This is the maximum value. So the global minimum is 17, which is what we found before. Okay, and then I can show you this nice little image. Nope, not what I wanted to do. Get rid of that. Get rid of that. And then you have this nice little image here. Okay. All right. And I was afraid we weren't going to get done with all 3. That's great. All right, so same basic premise for this last one. Part B. You want to find your partials. Set them equal to 0 and solve. So solving for this system, we get x equal to -2 and y equal to 3. So that means we have a critical point at -2, 3. If we plug that into G, we get -13. Okay. All right, so we want to take a look at this graphic first. All right. So the boundary of the domain of G can be parameterized using the following functions. So we have x of t equal to 4 cosine t. We have y of t equal to 4 sine t. And that is for t between 0 and 2 pi. We also have h of t, and that's going to be g of x of t, y of t. We're probably going to need some more slides. Okay, so I'm not going to do the in-between step because I just want to be able to squeeze this part on. So h of t ends up being 16 plus 16 cosine t minus 24 sine t. All right, so we need another slide. So what we want to do next is we want to find h prime of t and set that equal to 0. So we would have negative 16 sine t minus 24 cosine t equal to 0. So you end up with that gives you the tangent of t equal to negative 3/2. All right, this equation has two solutions over the interval. So again, we're looking at 0 to 2 pi. So one of the solutions, we'll just do it for both. Show you. So one of the solutions is going to be t equal to pi minus your arctangent 3/2. And your second one is going to be arctangent 3/2. Okay, so for the first angle, it's going to be okay. And then now you need to do the cosine. Okay. So we did all of that so that we could go back to x of t and y of t and now have them a little bit better. So now you would have, let's move this up a little bit. X of t is going to be negative 8 square root of 13 over 13. And then y of t would be 12 square root of 13 over 13. Okay. So then that would give us a critical point at that. So this gives us another critical point at negative 8 square root of 13 over 13, comma 12 square root of 13 over 13. Right? If we plug that into G, which I don't have enough room to do on here, so I'll just do G. I'm not going to work out the intermediary stuff, but you end up getting a negative 12, 8, 4. Okay. Oh, now we have to do the second angle. Cosine of t. Oops. I'm a little dyslexic on a couple of those. That's going to be 2 square root of 13 over 13. So if we go back to our 4 cosine t and 4 sine t, I'm just going to do it on this page. We didn't have enough room on the other. So your x of t would end up being 8 square root of 13 over 13, and your y of t would end up being negative 12 square root of 13 over 13. If you shove those into G, you would end up with 44.844. All right, so we have an absolute minimum at negative 13. So our negative 13 will be our absolute which is an interior point of D. The absolute maximum of G is the last one we just found. So that's going to be 8 square root of 13 over 13 and negative 12 square root of 13 over 13. That's going to be your absolute maximum. Oh, tell me this is part B. Which is attained at the boundary point. Okay, so then we can just look at the figure, and I believe we're done with this section. I would love to move that, but all right. So there you have that for those two sections.